So these were the objectives we defined in our phase 3 proposal. Yeah, so the first objective was to adopt an international validation strategy that would allow the community to identify knowledge gaps, improve models, and prioritize research efforts. So I have put this as partially achieved because it's true that we have been able to identify knowledge gaps, and we did this through mind mapping and peer analysis. But the outcome of the peer analysis was a bit so that this was not clear prioritization, since there were too many important phenomena that require validation. So some of them have been covered in AWAKEN, so I think that's how you can see this working out. But out of the expert elicitation process, we could see that there was really a lot of phenomena without a clear ranking on which ones should go first and so on. But still, we have some tools to discuss knowledge gaps, which I think is interesting. The validation activity has followed the validation plans of established in the European Wind Atlas and A2E research activities. So we've done many benchmarks with all of those experiments, and there are more to come. Of course, the data is not exhausted yet. Derived best practice guidelines and a model evaluation protocol. Well, we've moved forward the wind energy model evaluation protocol, which will soon be published. And we have included a number of open source model evaluation scripts, which is the best way to make evaluation guidelines for models, because people can actually use the evaluation tools directly. We have promoted open science benchmarking. So as I said, some of the benchmarks have used an open access scripts and data repositories. And this is going along the FAIR principles of the European Commission of publishing data that can be findable, accessible, interoperable, and reusable. So this is kind of the principles that should be used in general by scientists. And we are adopting this in Task 31 too. Unfortunately, we haven't managed to put together a benchmark for uncertainty quantification. So this fall out of the program, but it's nevertheless a very important topic that should come in the next phase. And then engage with industry. This is, of course, a very important objective for the IEA in general. And we had targeted 2 ISE working groups on wind resource assessment, site suitability, and numerical site calibration. We managed to do a benchmark with the numerical site calibration working group. And we have also managed to do an industry-driven benchmark together with the offshore wind accelerator that dealt with array efficiency prediction. So those were the 2 main highlights in terms of industry involvement. Now, in terms of technical highlights of the project, we have been able to achieve 7 different benchmarks on wind conditions and 2 on wakes. And the one with the offshore wind accelerator had 5 offshore wind farms. So very productive benchmarking activity this year. Some results from the most recent benchmarks. Swift, this is a benchmark on a single turbine and trying to reproduce the wake as well as the inflow and turbine response from this scale wind turbine site in Texas. And I have highlighted here that we could see how the model performance tracks model fidelity. This is important because this was something that we could not see in previous benchmarks. So if you remember, we did in the past the SGRE experiment, which was also dealing with a single wake validation. And in that occasion, we didn't find this type of consistency. So I think it's very nice to see that happening in Swift, which is probably not only due to more maturity in the models, but also because the data is actually much better. Now, the Wind Accelerator Wake Modeling Challenge gathered 11 participants, and the challenge was about predicting the array efficiency on 5 offshore wind farms. We're using mesoscale data as input, and then SGRE data to perform the validation. And we could see that the engineering models did generally a good job predicting array efficiency. So with bias within, let's say, 3% or so. But we could see that this was done through error compensation between turbines and between stability classes. So maybe the next challenge for wake models is to see whether we can actually be more accurate at local level, at site level. Now, I will not discuss too much about the LX17 benchmark because there's a presentation about this, but let's just say that it was giving good results, and we could see how mesoscale forcings and boundary conditions become actually more important than turbulence modeling based on the results we saw in this benchmark. Another case that we will see later today is about the numerical site calibration study at the Alaiz test site. Here we saw that the bias was a bit larger than we expected, more than 5%, which indicates that there's maybe potential lack of model maturity, or maybe it's also that we need more sites to confirm the results. So of course, this is just the first exercise on numerical site calibration that we have. So probably we need more data. The same goes for the Perdigao comparison of metrics microscale challenge. The idea here was to test metrics to map model skill versus cost and to inform model selection in wind resource assessment. So this was kind of the prototype to see if we could reproduce this curve of skill versus cost. The data from Perdigao seems to go in that direction, but it looks like we need to fill up the gaps here just to make sure we have all the range of the skills and cost in place to build this smart metrics. Again, another presentation later today is on the American Wake experiment, which is in the planning phase. Will start in 21 and we complete in 2024. So this is something that we plan to have extensive activities in the next phase of Wakebench. In terms of deliverables, as I said, we have been very productive with benchmarks. We are now finalizing the wind energy moderation protocol, and we are still busy with that. In the list of deliverables, we had a white paper, which we haven't really started. We started some discussion that this could be a good opportunity to reframe task 31 towards a more industry adoption, because this is what phase 4 is about. So I would like to have inputs from the group on participating in this white paper and see how we can put together a nice document that would guide the activities in phase 4. So my idea here is to engage with industry stakeholders to define the key challenges and requirements, and then with the developers of models and in general to see what would be the best solutions to achieve those requirements. We also seek more involvement with industry, and with them, there's always this idea of them facilitating access to data that we can then use to produce golden benchmarks for validation that can be used to support IEC standards. These are the elements of outreach and dissemination, a number of meetings. We have also had a newsletter and a blog, also a YouTube channel, and then we've presented in a number of conferences, and we try to publish everything we can open source, and we use Zenodo and GitHub as our default repositories. So to finalize, these are the conclusions I have put in the kind of the final management report. So I think the third phase of task 31 has been the most productive in terms of quality and quantity of benchmarks. We've made good progress in setting fair principles towards open source documentation through WeMap. But of course, we need more engagement from the community towards like a fully adopted project. I think we have reached a good level of maturity for to deliver high quality scientific benchmarks. We've been able to advance in meso microcoupling, to performance and wake dynamics, atmospheric stability effects in complex terrain, and also forest canopies. So all this is very important for flow models. We had more engagement of industry with 2 industry-led benchmarks. We've done expert elicitation using mind maps and peer analysis, and this has been used to inform the AWAKEN experiment, which will be useful to feed the next cycle of model development and validation activities in the next few years. And as I said, uncertainty quantification is remaining as an outstanding issue, so we need to address this in the next phase.
Okay, thank you. So hi everyone. In case you don't know me, my name is Barber. I lead the wind energy group at the Eastern Switzerland University of Applied Sciences, and I'm going to talk today about our simulation challenge, which is called Comparison Metrics Microscale Simulation Challenge for Wind Resource Assessment. First of all, I'm going to tell you a little bit about the overarching project we're doing, because this challenge is part of a larger project. And it's about, as Javier already said, developing a new decision tool for choosing the most effective tool. We've actually called that a wind resource assessment workflow now, because we've seen that it's not just about the wind modeling, it's about all the other steps as well. So I'll tell you about the problem and what we propose as a solution, then about the project, and then I'll go into the challenge itself with an introduction, and then an update of stage 1, and we want to tell you about stage 2, which you can register for actually now. So the problem is that there's a wide range of different tools with varying accuracies and costs, but often the choice has to be some sort of compromise between accuracy and cost. So how do we choose this? And our proposed solution is predicting costs and skill. So skill is like the accuracy, trying to predict with some scores before carrying out simulations, so that modelers can decide the most cost-effective model. It might look like this. So if we think of skill on the y-axis and cost on the x-axis, you can imagine, okay, usually tools which cost more money are likely to be better. So you see an increase. These different points are representing different tools. But at some point, there's kind of a flattening off. So you put more and more money in, but you don't get much more accuracy. And so we kind of see, okay, there's probably some sort of compromise of the most effective solution. The red parts, which we've marked on here, could be limits identified by the modeler. So maybe as a company, you're basically saying, okay, I don't want to pay more than a certain amount, or I don't want to go below a certain accuracy. So the idea is to develop a tool which allows modelers to be able to predict in advance the most cost-effective tool. And so the project that we're doing looks like this. So from left to right, we started by having a little look at Bowland Hill, because that's a project for which lots of data is available. And then we defined some parameters and so-called comparison metrics, which I'll go into in a second. And we defined how the process should work. And then we applied this process to 5 different sites. So within a separate project, we looked at 4 sites. And then we did the Perdigao site as part of this IEA task as well. And then we've used the results to design a decision tool, and we actually want to use stage 2 of this comparison metrics challenge to test this new tool. And so it doesn't matter if you can't really read this. I don't know if you can, it's quite small, but I just want to sort of tell you what these parameters are. So what we did is that we asked people in advance some questions about their setup. So we asked skill questions like, what is the complexity of the aerodynamic equations, or how good is what's the quality of the grid, what's the y plus value, are you within the operating envelope, is it properly converged, etc. And then part B here is the input data quality. So we asked some different questions about the quality of the input data. Part C is we asked some questions about the calibration and validation methods that we used. Part D is related to the annual energy production calculation. So what method was used to do that? And then we had some other parameters regarding the skill of the user and also the robustness of the model. And then we asked some things about costs as well. So we asked about software costs, the time to learn and the training costs, the simulation setup effort costs, simulation runtime costs, and post-processing effort costs. And what did we do with all these? First of all, I want to tell you one other thing. We also tried to classify the complex terrain, because we think that this prediction of the best model is probably dependent upon the complexity of the terrain, or of the flow, let's say. And so we developed some questions, and they were based on some quite a lot of work that Andy Clifton's done on complex terrain and LiDARs. But it was also based on the IEC 61412. But we wanted to ask questions that people could actually quickly answer and not have to calculate. So we asked some things about how many slopes there are, how steep they are, how many different surface roughnesses there are, also about the atmospheric stability and the degree of turbulence. But the idea was to sort of make a guess about that, or an estimation, and not do a big calculation. And then, okay, this is a big process, but it's basically just trying to show you what we did. So we kind of defined these parameters that I just told you about, and we also defined like weightings for them, because some of them we think are more important than others. And then the users on the left and on the right here, you can see they had a Google form which they could enter all these scores for each model. And then what we did, we calculated the weighted skill scores, and then we calculated also the total costs. And then on the left here, we averaged the weighted parameters to get a skill score before, like a predicted skill score. We then calculated the percentage of that relative to the maximum of all the different models. And we did it for wind speed, and then we did it for AEP as well, like separately. And then moving on to the right, we calculated these scores as a percentage relative. We calculated the cost as well as a percentage of the maximum. And then further to the right here, we actually entered the wind speed root mean square errors between the simulations and the measurements in order to get the actual accuracy. And we calculated that as a percentage score as well. And the same with the AEP, which basically allowed us to plot relative skill against cost, both before as a prediction and then after what the actual skill and costs were. And then we can see how good is this prediction at plotting this curve. So that's what we did. And then, so going into the challenge itself, this challenge itself now. So the goal of the challenge was to collect these inputs from many users, because the project we're doing has got 3 people involved, and we thought, okay, we get lots of inputs from the community in order to get much more data, so we can compare the estimations before and after. And so we split it into 2 stages. So stage 1 was the Perdigao site, and our imagination was that we would get something like this, where we could somehow transfer the predictions before to the actual scores. And then stage 2 is an open project, which I'll tell you more about in a minute. And so going to stage one, I guess I've introduced this before, but if people who don't know, Perdigao is in the middle of Portugal. It's got these two parallel ridges. And there was a very large measurement campaign in 2017. If you don't know about that and you want to know more, there's a very nice link here explaining the whole setup. This picture is showing these two ridges, and it's kind of showing all the different measurements. And we've actually picked the tallest masts, so 29 as the reference, and then 20 and 25, which are both 100-meter masts. Okay, that circle's in the wrong place, but as validation positions. And then there's also a wind turbine. Unfortunately, we couldn't get any data for that wind turbine, so we couldn't really use that, but we're still comparing the AEPs between the tools. So that's Perdigao. And then these are the submissions we received. So we had, some of them were anonymous, as you can see. And so we had some large eddy simulations. We had some CFD with different meshes and with different turbulence models. And we had some WASP simulations and Meteodyn. And then what we've done is basically we've plotted the root mean square error between the simulations and measurements for different masts. So first we've done it for the input, for the calibration mast 29. And what you see on this plot here are the different colors are all the different simulations. So some groups submitted multiple simulations with different setups. So you can see, for example, Organisation 8 had 6 different ones. And these 3 different groups are basically different root mean square errors. So because we had measurements at different heights, on the left you see we're calculating the root mean square error over the whole profile from the ground to 100 meters using all the measurement data. In the second one, we're actually removing the lowest point because that was actually very inaccurate, and it kind of had a big effect on the results. And for the wind, obviously for the energy production, the lowest point isn't very important. And then actually on the right, we show the results for the hub height, so that which obviously the errors are then much lower. And then you can compare. We're comparing each value to the mean of all of them. And then we've done the same for METMAST 25 and METMAST 20. So you can see that, I won't go into it right now, but you can see various differences between the models. And that's METMAST 20 as well. What else we've done is for example, we've plotted this root mean square error for each wind direction sector. So you see these polar plots. So this is an example for METMAST 29, where you can see, okay, the different colors of the different simulations, or the different colors of the different RMSEs, depending on the height, and the dotted and the full lines are basically the 2 separate simulations that these people did. And you can see it for METMAST 29, you can see it for 25, and there's various things that you can see, which I won't talk about in detail now, but you can see, for example, for 25 that there's wind from this northwest direction, which has a massive difference between simulation 1 and 2, and that was actually the canopy model being used. So obviously we need to look at that in a little bit more detail to understand what's going on. What we also did was that we looked at the speed up factor between the different METMASTs and the calibration mast. So on the left, this is just an example for one organisation. On the left, you see METMAST 20. The blue line is basically the speed up compared to the calibration mast from the measurements. And on the x-axis, we're seeing different sectors. So we see for different sectors, we have different speed up. And the red and the green and the orange lines are then the different simulations. So you can see, for example, in this simulation, the trend is followed actually of the speed up is followed quite well. The bottom is showing the shift, so it's the wind direction shift. You can see METMAST 25 has got, that's the one that's in the valley, and actually the flow has turned a lot inside the valley, and so you can see the measurements have got in certain sectors of like 40 degrees turning, and the simulations don't really pick pick that up at all. Yeah, and so basically there's lots of things for us to continue to analyze about the details of the flow, but the main thing is this comparison metrics chart. So I just want to give you a little look into this. So what we see here, I know there's a lot of information. We see the skill against the cost, and the different colors of the different tools which were applied. But the important thing is to compare before and after. So before are the white diamonds, and after the filled diamonds. And the whole point is that we're trying to get before and after to be the same, so that we can actually well predict what's going on. So you can see various things on here. For example, you can see that quite a lot of simulations are kind of bunched up towards the left, and there's one which is very much more expensive, which was the LES, which is not necessarily a surprise. I guess what's maybe surprising is that the accuracy is then not better. And actually we do see this kind of shape that we were expecting, an increase and then a flattening off, but then actually a decrease towards the right. Obviously there's much more analysis to do on this, but one thing that you can say now is that the prediction is basically telling us that this organization 8 is the most effective, because it's got very low cost, but it's still got a reasonable skill. And for the reality, it's kind of undecided, but let's say it's more like the blue one. So it's more like, it looks like organization 1 has actually got the most effective. Organization 8 is also quite high up there. So in that case, the conclusion would be that the tool has kind of worked, but maybe needs some improvement. And the same for MetMass 20. You kind of see a similar behavior. And again, the prediction basically predicts that organization 8 should be most effective. And in reality, it's kind of difficult to see, but you get a bunch of the blue and the gray and the green ones are kind of bunched up to the top left there. And so again, the tool has kind of worked, because organization 8 is also pretty good, but there's a couple of parameters which have not been predicted perfectly. And so we're looking at that a little bit more, and we plan a presentation at the WESC in a few weeks with more details on that. Just about the terrain classification. So this is really a blind test. So these organizations just filled in this form, and the average complexity was found to be 51%. The maximum deviation of this organization 5 is 20% from the mean, but the other ones are actually quite similar. So we need to look at that in more detail, but actually the results from the 4 other sites show a quite interesting effect. So what I just want to do is quickly summarize the results from Perdigao, but also with the other 4 sites, which we'll present at WESC as well. Basically, you can use this prediction to decide which tool is the best, but it doesn't work 100% perfectly yet. So yeah, we need more data. We really see, and I'll present this at WESC as well, that the quality of the tool, so how good it is at deciding which the best workflow is actually inversely proportional to the terrain complexity, which is probably what we would expect. And therefore, actually, the conclusion is that these parameters should be weighted somehow according to the complexity. So if there's a high complexity, there's some parameters which should be changed in order to improve the prediction. Predicting complex terrain with these subjective questions is actually quite difficult. The results I just showed you weren't bad, but from the other 4 sites, it was a little less good actually. And also this self-assessment of the parameters leads to inconsistencies. So we basically ask people to make their own judgment. And so what we want to do in the next stage with our new tool is we want to actually transfer the facts, like how was the model set up, to the skill and cost scores ourselves, instead of asking the users to make the predictions. And we also want to include some confidence scores in our predictions, so that people can still enter information even though they don't know how the model is going to be set up yet. And then the results will just have a certain error on them. We need to improve this way of classifying complex terrain, but as some of you know, it's quite a big, difficult topic. And then we need to include some weighting of the factors due to the complex terrain classification. And so we've basically sort of drafted a new tool, which will, on the left, take some user inputs about the site, the model, experience, the costs, but also maybe give some optimization constraints. Like, what does most effective actually mean to you? Then we have the tool itself, which will be classifying the complexity, calculating the skill scores, which will then be actually connected to the complexity class. It will be calculating the confidence class of the skill and cost, and then we'll have a final skill score, a skill score confidence class, a cost score confidence class, and then we'll make this plot, and then we'll make the decision, which will be a bit affected also by these constraints. So we're currently actually building up an automated tool to do that. So that brings me on in the last minute to stage 2. So actually what we want to do in stage 2 is we want you to submit results of already existing simulations. So we didn't get that many people participating. It was quite difficult to get people to do this task. And actually there's lots of literature and lots of people who've done simulations already, but don't necessarily report on the costs. And so what we actually want to do is get all these people who've all done these exciting simulations already and enter the details of the site and the setup and your experience, but also some estimations of the costs into a predefined template, and also give us either the measurement and simulation results or an assessment of the actual accuracy. And then our decision tool will estimate the skill and cost scores using these predefined parameters, and do the terrain classification. We'll then compare the results to the actual skill, and that will help us refine the whole process. We want to run the challenge on our new platform, which is called the We Do Win platform, which is basically trying to get people to collaborate together on real industry challenges. And so once you sign up for this challenge, you get access to the platform, and you can use that to like talk to the other participants and share ideas and interact with them. And so I'll put the link in the chat in a second. So I really encourage you to take part, especially if you've already done simulations and it's not that much effort for you to provide us with a little bit more information. So thank you for listening, and I'll be happy to take any questions. Thank you.
Thank you, Sarah. Right on time. I don't see any questions in the chat, but maybe someone wants to ask Sarah a question. Well, then I'll go ahead and ask. So you did Bolon as a first test, and then you have Perdigao. Is this progressing in the way you would have anticipated, or is the spread too large? Is the complexity of complex terrain too complex?
Yeah, I mean, actually, so I do have to say that the results of Perdigao by themselves it's quite difficult to use by themselves. So it's actually that combined with the other 4 sites which I mentioned, which actually make the results much more useful, because then you can see, for example, this inverse proportionality with the complexity. And actually, the Perdigao results haven't been included in that statement yet, so I'm hoping that that's going to fit into the trend. So yeah, it is helping, but we really need more data, and this is why we've got the stage 2 of the challenge. As you know, we've talked about it before. It's very difficult to get these predictions, especially when people are involved in it. So we are learning a lot, but we definitely need to get more results.
Sure. Okay.
Someone's raised their hand, I think. I can't see who it is. But...
Oh, yes, Herbert, go ahead. You have a question, Herbert? Yeah, maybe not. Okay, well, you can use the chat and put your questions there. Sarah will be.
I just put the link in the chat. Somebody just wrote, "How can I register to participate?" And actually, the link is directly above it in very big text for some reason. Yeah, if you click on that phase 3, phase 2, there's no phase 3. If you click on that link, you see that you can sign up. And so what happens actually when you sign up is that nothing will happen for a few weeks. You'll get a thank you email, but you'll get access at the end of the month. So look forward to seeing you all on there.
All right. Well,
Thank you.
Sarah. Let's move on to Johan. So Johan is going to present us the Hornamossen benchmark, the first results.
Thank you, Javier. So I hope that you can see my screen. I'm not familiar with Teams, so we'll see how this works.
It works.
Okay. Yeah. So I also like to thank Javier for inviting me to present, and also for pushing together modelers and experimentalists to do these benchmarks. I think it's really great for the community, and I think, at least for me, I really learn a lot in the process as well. So this benchmark is a diurnal cycle benchmark, and it is a part of the NEVA project. So the background is that there is this increasing interest, of course, for wind energy in complex terrain, and we have there large model uncertainty, especially if we have forested terrain as well as complex. And we also perceive that there is a lack of best practice, and as we already talked about today, the uncertainty quantification is also a big problem, but something that Sarah I think made a good improvement on, actually, and it'll be interesting to follow the results forward there. So we had an initial benchmark in Rinningsnäs, which is a heterogeneous forest but rather flat terrain, and the conclusions from that was really that using plant area density profiles from airborne laser scans could reduce the subjectivity and therefore the uncertainty a lot when it comes to the roughness of the lower boundary. So that was a great success. On the other hand, it was clear that it was difficult and challenging for the modelers to model anything but neutral stratification using that technique. And also looking at the results, it is clear that modeling non-neutral stratification is really essential for realistic results. Because, well, simply all results or a long temporal average doesn't average to neutral simply. So after that, there were several benchmarks launched within NEVA, and they were in this direction of investigating complex terrain and forested terrain. With Kassel, for example, Hornamossen and Perdigao, that has already been mentioned, and Alaiz, which we will also see results from in the future. But this is Hornamossen. So the specific aim here is to evaluate the NEVA model chain, or, well, a model chain actually, and how it performs in complex terrains with a heterogeneous forest, and that is really the key here, for relevant atmospheric conditions. And in order to map the relevant atmospheric conditions, we thought that it would be nice to simulate the whole diurnal cycle to sort of get the whole span. The site is located in southern Sweden, in between the two biggest lakes, and it's on a hill, but it's not a mountain, so it's a rolling terrain, so to speak. But as you can see on the on the satellite image here, it's really forested, but typical for Sweden, it's patchy forest, so you have clearings mixed with 100 years old, 30-meter high trees. And the instrumentation at the site looks like this. So we have here also the topography, so you can get an idea on the terrain differences. And this was different from the other NEVA sites in that we didn't have a scanning LiDAR here. So this is a more traditional with the profilers and tower measurements. But we had quite a few profilers, and we placed them on sort of a line from left to right in the figure, which is also then from west to east, to map the flow as it goes over the hill. And we had a tower in the middle, which was 180 meter high and quite well equipped with sonics and cups. So we have both more traditional wind energy directed equipment, but also more research directed equipment. So on to the benchmark itself. We manually scanned the long-term measurements at this site and then found 2 periods with quite stationary conditions and strong diurnal cycle, meaning that the flow isn't too strong or too windy, and the skies are relatively clear, and the wind direction stays more or less constant, as well as the wind speed for a couple of days. And today we're going to look at some teaser results, or a tease of the results for the east case only. So we'll leave the west case for now. This is a case where the eustrophic wind was around 12 meters per second, and the wind direction at 100 meters is roughly from well, it's actually the wrong wind direction, so it's around east, so 90 degrees. The idea is then that to test the model chain, we start with the NEVA WRF model, so the settings in WRF that was used in the NEVA, and this is the 3 kilometer resolution, and that was then providing transient boundary conditions for the modelers. So this is input to the modelers, and then we asked microscale modelers using URANS or MESO NVP or even LES to model this site using the boundary conditions from WRF. And the reason for not using the measurements directly as boundary conditions was to test the whole model chain in the New European Wind Atlas. So first step is then to just check, do a sanity check on the and assess how well does WRF actually compare with the measured boundary conditions. So we try to at least get a grip of how large false errors do we get, because the WRF is actually off. And then finally, which is the sort of interesting part, is to validate the microscale results with the measurements, and that is what we're going to mostly focus on today, and try to get some quantitative results, not just qualitative in terms of flow patterns and so on. So we quickly turn onto the WRF results. So you see them there in blue, and the measurements in black, and these are 1 hour averages over the 3 days for the east case. So surface fluxes are reasonably well predicted, as you see here. U star representing the momentum flux above, and then below we have the heat flux. And they qualitatively follow each other, but there is some difference in the magnitude. So if we look at the Z over L, where L is the Obokov length, we can see that there is actually a larger amplitude in the momentum flux, or in the stratification in the actual conditions rather than the WRF conditions. But remember that the modelers they only see the WRF conditions actually here. So since not all models have the possibility to model a transient simulation, we also split into sort of more traditional stability classes. So we have unstable data. These are just all the periods with where the phi function differed more than 20% from its neutral value onto the unstable side. And then we have neutral, which is then allowed a 20% variation in the phi function for momentum, and then the stable conditions. And in order to test the long-term temporal average, we simply did an average over a diurnal cycle, and we choose the middle of the period for this diurnal cycle to minimize the effect of any speed up in the beginning of the simulation. So on to the results. These are the wind profiles at the position of the tower, and you can see the different models here on the left. So they are ranging from NVP to LES simulations, and the measurements with the 95% confidence bounds, well, estimated 95% confidence bounds, are in white with error bars. And what is immediately detectable is that you have this, as we can expect, difference between unstable and stable conditions with a much lower shear in the unstable conditions. The diurnal average look pretty similar to the neutral average here, which is a fact of that the simulation is slightly biased towards unstable stratification, because this was in the summer in Sweden, and that means that it is almost day the whole day around, so to speak. The sun is up between around 4 to 8 in the evening. If we look at the wind direction, we can see some differences between the models now, especially in stable stratification, where we have this very large veer in the measurements, which is picked up by some of the models. But all of the models qualitatively follow this behavior. You can also see that measuring the veer with the tower instruments is not that easy. Now we turn on to turbulence kinetic energy, and here we can see actually that even though the models on average are doing fairly well, there is an underestimation of the turbulence kinetic energy in unstable conditions and an overestimation in stable conditions. But this could be an effect of that the diurnal cycle is actually a larger amplitude in the measurements than in the WRF simulations. On the other hand, the WRF simulation is actually the one that to the best extent captures the turbulence magnitude of the measurements. So it could be something else as well. When we look at the flow over the topography, these are the results. And here it's important to notice that the flow in this case is actually coming from the right side of the picture, going over the hill to the left. So if you think of it as well, I wasn't sure if I should plot the wind profiles on the negative side of the origo, but then I opted for this standard way instead. But just remember that the flow is coming from the right side, going to the left-hand side. And here, in both in different conditions, like unstable, neutral, and stable, the models do a fairly well job capturing the differences. They can pick up on things like the really low wind speed on the lee side or on the front side of the hill, and lower wind speed also in the small valleys in between the crests of the hill. For turbulence kinetic energy, we see an even larger cycle, so you can clearly see the difference in magnitude between unstable, neutral, and stable conditions. But again, as I already stated, that the models have a lower amplitude of the cycle here than in the measurements. So to highlight the effects, we also plotted the actual cycle. So these are 1 hour 1 hour averaged wind profiles, and some models are not present here because they didn't submit results that were transient, but rather stationary result in different stratifications. And it's interesting to see the large differences on the cycle, and actually that even though these models, they are ranging from runs models to MVP models to Alaiz models, and the boundary condition for stratification was different in all of the models, and they are still looking fairly similar actually. So it seems that the most important thing is to model stratification, and how you do it is to some extent less important. We can also take a look at direction, and here one interesting thing to notice is the very large deviation of, so let's see, now my screen froze, but I hope it works for you guys. The very large deviation in wind direction on the front side of the hill being the profile to the rightmost profile in the night, and also the really large difference in veer between the night and the day. And here again we see some larger deviations between the models, and this is something that we need to examine further. But it is for sure an interesting result, and it indicates that fraud number effects might be quite important, even though this hill is actually quite mild. So if we look at the TKE, we can again see that we have this large cycle, and the models are for the most part actually doing things that look quite reasonable when we see the evolution of the turbulence kinetic energy, and how it varies over the day. So since this was only a teaser of the results, this benchmark have been quite challenging actually, and it's been very difficult, as Sarah also mentioned, to get participants to the benchmark, and one reason for that is probably because we required modelers to be open with the results, so we didn't accept the anonymous submissions. But another thing is probably just that it's quite challenging to model stratification and explicit forest at the same time. So this is a first look at the results, and therefore it is concluding for this presentation, but it's really only initial remarks. So we hope to really kick off the interesting research from here. So the first conclusion seems to be that it is more important to actually model stratification than how you do it. So comparing to just model neutral stratification, it is really a big advantage to just add stable and unstable. And if you could do the whole cycle, it's even better. But the important step is to include stratification at all. And then also that a lot of work is remaining. So we need to quantify the results, not just look at the qualitative behavior, but actually do some plots with the confidence estimates as well, so that we can draw clear conclusions from this benchmark. What is, for example, the difference between the directions? Here we only look at the east case, but of course we will also examine the west case and how they differ between each other in terms of speed ups for different places, for example. So we will move on from here with the detailed comparison and assessment, and then meet with discuss the results amongst the participants, and then hopefully we can compile a paper and publish the most important findings. After that, this benchmark and the validation data and even the long-term measurements will be published for open use within the community, and we really hope that it will be of use as well for a long term in the future. So that was all from us in Sweden. So thank you very much for listening, and so please don't hesitate to contact us if you're interested in learning more about this benchmark.
Thank you very much, Johan. This has been very exciting to see. After so much work going on with experiments and all the models, it's really nice to see the results of the benchmark. Is there any question from the group? I don't see them in the chat. So we are in a similar stage in the Alex 17 benchmark, and you will see next our results on mean profiles of wind speed. We don't show results of turbulence because they are still fresh, I would say, but it seems like we need to address turbulent kinetic energy from RANS models, especially. Because I remember from your RINIXNAS study that there was some improvement when calibration of the constants was allowed, at least for some of the participants.
It is scary how sensitive the RANS results for turbulence kinetic energy is for different, well, seemingly very small and also logical deviations of the closure constants, and then they can have huge effect. The upside seems to be that it doesn't really affect the wind speed and direction so much, but for the magnitude of the TKE, it really makes a big difference.
Yeah. I think Matthias has a question. Matthias?
Hello. No, I about the turbulent kinetic energy. Yes, I was like seeing that that the RANS under predicts during the daytime and over predicts during the nighttime. Yes, but I was thinking that maybe it's a good idea to add to the RANS, because something is happening to the URANS that you obtain a large fluctuation of wind speed, of velocity, so you can add a resolved turbulent kinetic energy, and maybe maybe adding this resolved turbulent kinetic energy, the results are better, obtain a better prediction during the daytime. But it is very strange that during the nighttime, the over prediction of just only the modeled RANS turbulent kinetic energy.
I think that's a very good remark, and actually there are lots of points that are not trivial in this, even from the measurement point of view. So, for example, for this benchmark, I took the 20 hertz data for the whole 3-day period, and then I high pass filtered so that only variations faster than a period of 30 minutes would appear in the turbulence kinetic energy to get a fairer comparison with the RANS data. But of course, that cutoff between the trend in the URANS and what goes into the turbulence is not clear, and it is certainly a function of stratification as well. So these are interesting open questions, I think.
Sure. Yeah, we are kind of in the same level, Alex. 17.
And it seems like RANS is like capturing scales that the RANS shouldn't capture. And it is like, if I don't know if we should be confident about all the scales that are appearing during the convective boundary layer in the RANS. I don't know. It will be nice that more LES models can participate doing the diurnal cycle, just to compare the turbulent kinetic energy. Yes, maybe to make a better comparison, a detailed comparison or something.
Yes, something we could do is to put the two benchmarks together and start discussing the similarities we see in both Alex 17 and Hornamossen, because I think this is interesting to see that if we can find consistent results in both, that can allow us to kind of reduce the complexity of our conclusions, right?
Certainly, that seems like a good way forward.
Okay. Well, if you have any other questions, please put them in the chat. I will go ahead and start presenting the Alex 17 benchmark. So there we go. So as you see, this is a collaborative work with people from Ives, well, Pedro was former GTU, Roberto from UL, former SGRE, Matthias, Herbert and Oriol from BSc, Dalibor from GTU, and then Ru and Eric from Meteodyn. So the background, I put it in the context of what we did back then, the NEWA project with the Gables 3 benchmark. So that was used to test the meso-micro coupling methodologies in flat terrain. And you can see here in the graph how all the models arrived to kind of a similar diurnal cycle with a low-level jet in the middle of the night, and kind of good prediction of wind direction and temperature and too. So in that particular benchmark, we introduced the tendencies approach for offline coupling. So what this is that from WRF, we obtain the advection and pressure gradient forces directly from the simulation. And then we introduce this as volumetric forces in a microscale model. Models that you see here, offline coupling, and we could see that they provided consistent results comparing to other models that use dynamic coupling like Ventos or WRF LES. And in this particular case, we also arrived to the same type of results with mesoscale, because there's no microscale really added to the complexity here. So the objective now, as you saw in the Hornamossen benchmark, is to test if these methodologies also work in complex terrain. And that's why we have this setup of experiment in Pamplona at SGRE test site in Alaiz. So the Alaiz mountain range is here in the south, and we have one reference station that is kind of our target for the predictions. And then with the Alex 17 experiment, we deployed a number of 80-meter met mast in the valley and also in the lee side of this upstream ridge. We also have a scanning LiDAR trajectory, as you see here, but we are not going to see results of that yet. So the evaluation will be focusing on the met mast profiles. And we also use the NEWA WRF setup to come up with a reference mesoscale simulation that we can use to provide forcings to the microscale models. And these are the models participating. We have the WRF LES simulations that go all the way from 3 kilometers to 100 meters with an intermediate step mesoscale at 300 meters. Then we have BSc working with ALIA code with both RANS and LES modeling and using 1D tendencies like in the Gables 3 case. Then DTU with ellipsis 3D, two approaches, but essentially using the same type of boundary conditions than ALIA, but so periodic conditions, but now using 3D tendencies instead of 1D tendencies. And two approaches here. One of them is to update the simulations every 12 hours. So this is with the idea of refreshing the mesoscale forcing so that you don't allow the microscale to drift too much. So basically, we can test online versus offline coupling, RANS KL model, which is the one for Meteodyn. I forgot to mention this. So Meteodyn participates with a mixing length model, and instead of using a dynamical coupling approach, it's using a statistical coupling approach with steady RANS simulations. So we compare those with the URANS simulations, also with LES, so testing the turbulence model. And now we can also test 1D versus 3D, and then periodic versus nesting type of boundary conditions. This is the diurnal cycles that we are interested in. They all present a uniform wind direction from the north, as we measure that in the MP5 reference mass at Alaiz. And then we see that 4 consecutive diurnal cycles with relatively stationary forcing, where we can test the different modes. It's not so important to look at the time series, and you can already see some differences hour by hour. It's more relevant for the validation to look at how the models predict the different stability classes. As you can see here, we have defined these 7 classes. Although the last one, very stable, we will not use because we don't have enough statistical significance. We define this based on the M7 position, which is based at the valley of the right in the middle of the valley. Now let's look at neutral conditions. For reference, here's the MetMass layout, where you see M6 and M3 kind of at the lee of the Tajonar Ridge, so the wind is coming from the north. We have a number of masts in the valley approaching the Alaiz Ridge, and then we have MP5 at the top. So already when we compare the microscale simulations with the mesoscale, which is this purple line, you can see that all of them do a good job correcting the mesoscale bias in magnitude, but also in wind shear in general. And then we do a reasonably good job in the mass at the valley, but then when we approach the most complex side, which is this M6, which is right at the lee side of the Tajonar Ridge, which is rather steep, we see that there is more deviation. So the CFD approaches tend to cluster well along the measurement, so they capture pretty well the sheltering effect of the ridge. And we see that mesoscale models and WRF LES, well, as you increase resolution, you get better correction of bias, but they don't reach the results that we see in the other CFD simulations. And we attribute this to a lack of resolution, because WRF LES can only do 100 meters in this case, and the others could deal with less than 50-meter resolution horizontally. If we look into unstable conditions, here you see more spread in the results. So it looks like unstable conditions bring more complexity to the wind conditions here, but nevertheless we can see some interesting results at the top of Alaiz at the MP5 position, where ellipsis 3D could actually capture the negative wind shear that you can see in the top of Alaiz. Other models are kind of getting there, but well, in this case, ellipsis 3D was kind of the best one. As for stable conditions, so even though stable conditions are traditionally the most challenging in flat terrain, in complex terrain, it doesn't look to be the case, at least for Alaiz. And as you can see, the scatter has been reduced compared to the other cases. And something that is nice to see is, for example, this low-level jet developing in the upper part of the boundary layer, which is also present in the valley, of course, but when you have the speed up of the Alaiz mountain, you can see it approaching the measurements that we see there and generating this large wind shear that the models are capturing pretty well. Still at the M6 position, we still see the problems of resolution in the WRF LES model. And maybe something that we can also see is that the ALIA results, especially the URANS results, tend to show a larger bias here than what we could see in the other cases. And we think that this is maybe due to the influence of using 1D tendencies versus 3D, which is the case of ellipsis 3D. So as we know from the Gables 3 case, in stable conditions, the mesoscale influence approaches the ground level because the boundary layer gets shallower. So it becomes more important, the mesoscale activity, compared to the microscale already at distances of 100 meters or 200 meters. And we think that this could be the reason for these larger differences between ALIA and LYSIS 3D. So bringing this higher, this more detailed mesoscale data to the microscale makes sense for stable conditions. Now putting all of this together into quantitative metrics. So here we are computing the bias, the wind speed bias, for the different masts, and then for all of them together. So we start with the overall bias. We see that the reference mesoscale data at 3 kilometers has an overall bias of 32%. And then as we introduce more microscale, you see that the bias is reduced significantly. If we push the mesoscale to 300 meters, which is already within the limits of applicability of mesoscale, we see that we can reduce quite well the bias to 7%. And then as we do this with CFD models, we see that the bias is reduced below 5% in general, with Meteodyn reducing the bias to 0.5%. Of course, inside all of these overall bias, there's a compensation of errors between masts and also between stability classes. But we can see some trends from the different models. For example, if we look into the WRF LES results, we see that as we increase the resolution in the different nests, first in mesoscale, going from 3 kilometers to 300 meters, mitigates the bias in the valley quite significantly. Also in the MP5, so MP5 can be very well reproduced already at 300-meter resolution because the Alaiz mountain range is pretty large. So the mesoscale model can capture the speed up effects pretty well. But if you look into the M6 mast, we see that increasing the resolution improves slightly the results, especially in stable conditions, but it's still not enough resolution to capture the stable conditions. If we look at the results from Meteodyn, we see that the results are pretty good in general, and you see good compensation between stable and neutral and stable classes. And what we can see also is that the scatter of the results of Meteodyn compared to the other CFD approaches is also lower. Our hypothesis here is that is not because of the type of turbulence model. It is more because of the other CFD models using periodic boundary conditions that are kind of introducing spurious effects that affect the performance here. And then comparing ALIA with Ellipsis 3D, well, we mentioned before how Ellipsis 3D has a better agreement in stable conditions. But in terms of spread, we see that they both suffer from large variability. And this is probably because of the boundary conditions that are not the most suitable for complex terrain. So I think I'll skip the conclusions just to see if there are questions, but let's say that we are just starting to analyze these results, and there will be more coming up on turbulence intensity and wind shear quantification. And we are releasing all of these live in the GitHub repository. So you're welcome to take a look. And if you want to participate on this benchmark, you can still do it. Just reach out to us. So, is there any question from the group? Matthias, do you have a question, or is you still have the hand raised from before?
Hello, it's for now. It's for now. No, it's just a comment. No, just
Go ahead.
What I have seen is that in Hornamossen, the tendencies are like very uniform with gate. And with Alaiz, the tendencies are the hell, are very, yes. So maybe, yes, and what I think is that the results depend a lot of the tendencies of the work results and the tendencies and maybe of what you say about the non-homogeneity, the non-horizontal homogeneity, because another thing that I saw is that when I modify the temperature in the floor, I modify a lot the obtained results. So to have different temperatures along the mountains, such in a complex terrain, maybe it can help a lot to obtain better results. So yes, and our LES and our RANS models obtain very similar results. So I think it's a question of the tendencies of the mesoscale and of the kind of coupling. And this non-homogeneity maybe can help a lot.
That's also my main conclusion from this benchmark so far, is that mesoscale and boundary conditions, so your inputs essentially are way more important than turbulence modeling. We could see that Meteodyn reached the best results with a mixing length model. So until we get the boundary conditions and the mesoscale tendencies or the coupling in place, the turbulence model will not have added value, let's say, especially if you go into LES. Yeah, there was a question from David, if I recall.
Hey, Javier, just do you have a plan to publish this soon?
We plan to have a presentation in the Wake conference. And yes, it would be a plan to have a journal paper following up.
Thanks.
So Johan.
Yeah, this was also a comment on Matthias' comment and what you were discussing, and we've been discussing this a lot also. I think it's an interesting open question how to do with the tendencies, and especially if you apply homogeneous or homogeneous pressure gradient, or if it's allowed to vary with heights, because I guess having it varying with height can help break up any inertial oscillations. But on the other hand, having a pressure gradient varying with height is probably due to large-scale temperature gradients, horizontal temperature gradients in the mesoscale simulations, which you're maybe not inputting into the microscale simulations. So they are lacking there, and to get that right, maybe that is why Matthias is seeing these differences when he changed the temperature. But yeah, just to comment, I think it's really exciting to see these results and to hear your thoughts.
Yeah, I think we need to compare those mesoscale tendencies, see what do they have in common and what do they don't have in common, because then this really seems to influence a lot the simulations, especially in the stable conditions. Roberto, you have a question?
Yeah, hi, thanks. I think this is more like an open question for both you and Johan's presentation, which is related to the fact that is like have we thought in a way to produce like different metrics or more comprehensive metrics to validate these new cases, because it seems that connected to what Sarah presented, it seems that it's short. The current metrics are short on trying to concentrate or concrete the very rich full information with these new cases, Perdigao or Hornamossen or Alaiz, because it seems like in Alaiz, and it looks like it would happen the same in Hornamossen. You have so many masts at so many heights that the same model can be the best in one situation, in neutral case, but then worse in a stable case. So when you gather everything together, a bias score or a root mean square error metric can just lead you to misinterpret the let's say the quality of or the performance of any model. So I was wondering that, just getting back to what Sarah presented on this skill score, I'm not sure I get exactly the definition of that skill score, if it's like more the way it's defined in meteorology, but yeah, I think it's a big challenge. Just this, I think it's more like an opinion or open question, that it's a big challenge to use these newly highly with high quality data sets, observational data sets.
It's difficult to put everything into in a single metric. The one we use is the simplest one, and the one that is best connected to what a wind energy developer would be interested in. And of course, there are other use cases that would benefit from a metric that integrates turbulence and other quantities. So yeah, I think we need to discuss that and see how we can put together something more meaningful for depending on the use case. But the best metric available would be how much money am I getting from the additional accuracy of these models as a developer. That would be the best metric, if you can come up with that one.
Yeah, right.
Yeah, maybe we should adopt something like the Breyer score and compare to the WRF input data.
That's true.
Maybe that's a way forward. I think another interesting thing with regards to what Roberto was asking is also the uncertainty of the measurements, because well, there is random error, and then you have measurement error, and sometimes at least in Hornamossen it seems that it's difficult to draw any strong conclusions because of the just the inherent uncertainty and random error of the measurements.
That's true. That's very true. Any other question or comment? We will move on. If not, then Gang, you are up next with a Alaiz numerical site calibration benchmark. Are you ready to present?
Yes, but I couldn't see the request.
You can share your screen directly. I don't need to.
Yeah, okay. Yes, open share tray. Okay. Can everybody see my screen?
Yes, right there.
Okay.
Go ahead.
Cool. So yes, I'm Gang. I'm from Meteodyn. I'm very happy here to share with you the latest results of the Alaiz benchmark on numerical site calibration. So the objective of site calibration is find this flow correction factor between a met tower and the potential turbine locations. So in our benchmark, the objectives are threefold. The first one is to make sure to check if the state-of-art safety models are up to the task of predicting flow correction factors. Secondly, we want to collect some best practices in conducting and documenting the NSA exercise, which could be proposed to future AC standards. And lastly, we want to identify some limitations and experimental data sets for VNV that could be further addressed by future experiments. So this benchmark is supported by the Alaiz site calibration campaigns, which have 2 periods of measurements, the SA1 and the SA2, each lasting about 6 months. These campaigns are some short-term periods to measure the speed-up factors between a reference mast and some target masts. So here the reference mast will be MP5. We will see better in this map. The MP5 mast, Javier has described it in the previous benchmark, is on the north slope of the mountain, just before the hilltop. And the target mast, we have 6 target mass A1 to AC, which represent potential turbine locations. The objective of the benchmark is, as a blind test, is predicting how we transfer wind speed from the reference, which is MP5, to the 6 target mass. So I think it's important to note that there is something like a small ridge line between MP5 and the target mass. While we can say MP5 is on the north side of the hill, the target mass seem to be more like the lies on the south side of the hill. This may have some influence on the performance of the CFD models we will see. And here is the wind conditions measurements at MP5. We have mainly 2 dominant directions from the north and the south. So here we identify 10 wind sectors, and the participants are required to submit results for all the 10 sectors. Then we put together the 5 small sectors into a big north sector here, and we do the same. We define another south sector for the 5 Tengri sectors here, and we have done some classification of the atmospheric stability conditions. We separate wind into a neutral state, unstable, and stable conditions. And we note here that the unstable conditions are predominant here in the north direction. So since the kickoff webinar in June last year, we have 29 registrations. And as of February this year, we have 19 valid submissions of results from 11 participants. We have 2 LES rounds, 16 RANS rounds, and 1 WASP round. So we can see that we have multiple submissions. Often we have multiple submissions from 1 participant. The WT is a Meteodyn WT software using also the RANS turbulence model. So the main metric that we use to evaluate the numerical results is the mean bias, which is the relative difference between numerical values of the flow correction factors and the experimental values. So we use absolute values in order to avoid error compensation between sectors and the stability conditions. So here is the result with the ranking of the numerical results. The best results come from RANS, especially RANS 135C here gives the lowest bias, about 5.1%, so a little higher than 5%. We have a refinement of mesh between RANS 135A and RANS 135B from 20 meters to 10 meters, but it didn't bring any benefits in decreasing the bias. We have a WASP ROM, which gives a not bad result, but it's worth noting that it comes from the same author, which has also submitted another RANS ROM, which is the second best result. And we can observe that using the same tool, the bias ranges from 6.7% to 5.4%. So it depends on the user. And we have 2 LES ROMs, as I said, and LES 122A is more refined, uses a finer mesh, which decreases a little the overall bias, but on the whole, the results are not satisfactory. We will try to understand more later. So here I break down the overall bias at each mast. We can see that we have some similar behavior between A1 to A3, which are the three masts on the west side, far side of the mast, and A4 to A6, which are much closer to the MP5 mast. So we have a lower bias at these masts. And if we look at the mean bias by sector and the stability, and this time we define the bias with signs. So in order to show that in the north sector, the CFD results underestimate the wind speed at the targets because we have a negative bias. Whereas at the south sector, we have overestimation of the wind speed. So here the percentage represents the frequency of the sector. The north sector with the unstable condition is the main case. And here, from now on, I will choose to focus on the A4 mast, which is one of the nearest mast to the MP5. And here I highlight some, I plot the mean value of the experimental FCFs plus minus the standard deviation in order to show the scatter of the experimental data. It is the mean values that we use to compare with the CFD values. So let's look at the FCF profiles. Firstly, from the north sector. So the north sector in this Google Earth picture is from right to the left, and in fact, the wind, the mountain just we have a continuous rising of the mountain of 700 meters, and up to MP5, and then the wind arrives at the target mass. So the MP5 is in the upstream. So we can see that the A4 mast is close to the MP5 mast. So here is the experimental data. I show the MP5 profiles on the top, the A4 profiles on the bottom. We can see that we have acceleration of wind speed between MP5 and A4 for all three stability conditions. The acceleration seems to be more pronounced for the stable case. So here I keep the experimental data, which is in black, and I put also the numerical results. We can see that in general, the CFD models doesn't reproduce the acceleration of wind speed at A4, because each time we have this deficit of velocity, deficit of wind speed for all stability classes. At MP5, we can see that the RANS models match rather well the gradient, the wind shear, but this didn't help get the right speed up at the target mass. The error seems to be larger for stable cases, as you can see here. Yeah. So it needs to be pointed out that the LES simulations doesn't undergo a sufficient calibration, and at MP5, which can be guessed here, because it's due to the methodology of the simulation, which simulates a 4-day period at this micro scale level, which may not give enough sample sizes to be compared to unsteady simulations. So if we look at the south sector, the wind comes from left to right. So this time the target masts are upstream, and then we go over this small cliff and we arrive at the reference MP5 mast. Compared to the north side, we may have some more vegetations on the south side. So the question is, will the wind keep on accelerating from here to MP5? And the experimental data show that we still have acceleration from A4, which is upstream, to MP5. And this acceleration is true for all three stability cases. And if I add the numerical results, we see that the bias is lower compared to the north sector. For example, we have a blue line here with a RANS 135. It do a really good job of matching the wind shear at the target mast. Although the wind shear at MP5 is overestimated. Unfortunately, LES results are still off the mark. We have some over-predicted shear. Once again, yeah, it's a limitation of the workflow. We simply may not have enough samples to be comparable to the experimental results. So lastly, I want to show the turbulence intensity profiles. Just for illustration, it's not clear that whether all participants has done any calibration of these turbulence profiles, but the results are not so bad. For the most frequent case, the north sector unstable, we have good match between RANS results and the experimental data. But if we compare north and south side, we see that the RANS models didn't predict the higher turbulence coming from the south, maybe due to the vegetation. And as often, the LES results predict a higher turbulence intensity than the RANS runs. So if we return to the mean bias result here, if we try to explain this bias, this small ridgeline could be an obstacle in correctly predicting whether the flow keeps on accelerating between MP5 and A4. There is some vegetations. There are more vegetations on the target mass than around MP5. This may be a reason for the bad performance. And the third point is we have given information at MP5. We have multiple heights of measurements of wind speed, etc. But we somehow lack some information on how the flow evolves in the horizontal, how the flow evolves in the streamwise direction. So maybe this lack of information is crucial in creating this bias as high as 5%. But this is the task of NSC to predict this evolution. So some final thoughts on the benchmark. We have seen that the refinement for the LES results does bring some improvement, but not always, because here between 135A and B, we didn't see any improvement. What is more important for me, I think, is the calibration at the reference mast of the wind shear. It is necessary to avoid really bad results of the flow correction factors. And thirdly, I think a proper weighting of safety results using the MP5 time series is important. It is clear the participants that do not do this kind of analysis of time series do give bad results. So some open questions remain. we have seen that maybe the horizontal evolution of the wind, at least for the Alaiz site, seems to be less dependent on stability than maybe the vertical extrapolation. So maybe we need more cheaper unsteady simulation in order to confirm the added value for more advanced turbulence models such as LES, because now we didn't see any interest, any advantage of using LES here. And the third point is maybe if we can bypass the uncertainty of classifying stability classes by using simply high shear, medium shear, and low shear classes, and maybe we can lower the scatter of the experimental mean values of the FCF. So yeah. So clearly for SCFD models, we have room for improvement. We have 5% bias overall, and I think predicting a shear dependent sector-wise FCF puts a lot of strain on the numerical models. We have the expectation that the CFD models need to be versatile at all stability classes, and it needs to be cost efficient. As I think it's a it's more difficult than predicting a mean wind speed, for example, for an AEP assessment for an annual wind speed. So yeah, we have. I hope modelers can keep on improving the models, get feedback from our benchmark, and do better in the future. I want to give my thanks to Javier, which thanks for your guidance in launching and organizing this benchmark, and thanks to all the participants for following through this exercise. Thank you very much.
Thank you, Gang. It was really well done by you, so congratulations for that.
Thank you.
Is there any question from the group? I don't see anything in the chat or any hand raised. I have a question myself. So
yes.
So how does this leave us? Because it would have been great if we would have found 1% bias, and then all the industry would be very excited to avoid the costly site calibration with measurements. Is this calling for another exercise like this in a different site, or do you think we should continue exploring what we are doing in Alaiz to make sure we are doing the things right with the models? What do you see?
Yeah, I think there is a room for maybe improvement on two sides. I don't know much on the experiments side, but it would be great if we can decrease the uncertainty related to the stability conditions. But on the numerical side, we do see a systematic bias between the CFD results and the experimental data on all stability conditions. So surely we have some shortcomings in the numerical models, but it's hard to say which one, because we have many turbulence models. People have used their forest models, but still we seem to be stuck at this 5% bias. Yeah, I think maybe more effort is expected on the modelers side in order to improve their results. Yeah, I will put my hope to maybe unsteady models, but by focusing on neutral conditions, in order to see whether we can improve on the compare with the steady simulations.
All right. In the interest of time, I suggest we move on to Pat and present the AWAKEN experiment progress. Thank you, Gang.
Thanks.
There you are.
Hi.
Hi. Go ahead. We can see your screen.
Yeah, let's talk about the AWAKEN project. So the AWAKEN project is a large field campaign in the United States with lots of different entities and institutes. So we'll just quickly go through it and then how it relates to Wakebench going forward. Oop, there we go. So the goals are really to gather detailed observations of wind farm atmospheric interactions. To understand all the complex flow physics. This is actually an onshore experiment, so it will be one of the most detailed observation campaigns of an onshore wind farm. And we're focused on the physics kind of in the middle of the scales of interest in wind energy. So in between the mesoscale and the turbine scale. So we're not looking at what's happening at individual blades on turbines, nor are we looking at things like large weather systems. And there are actually two complementary field campaigns in the United States that cover those scales. So we're in between those two. So we want to understand the physics, but we also want to validate the models, which is highly related to what's going on in Wakebench. So we do hope to have a lot of benchmarks produced from this field campaign. And all of the data will be publicly available and to researchers worldwide. There might be some restrictions as far as power production data from the actual wind farms, but we hope to normalize those so that they can be shared more widely. Another side goal of this project is actually to advance the state-of-the-art of instrumentation used to gather field data for wind energy applications, because we know that the resolution of a lot of our instruments is now more coarse than the simulations that we're validating with this data. So if we can get higher fidelity observations, that will certainly be of use to not only researchers, but also the industry in the future. So just to give you an update of where we are, we've been doing just a lot of planning for actually the last 2 years, building up to this project. The project is due to start in January of 2022, so we're about 7 months away from actually deploying instruments. So lots of agreements, also trying to engage different partners so that we can widen the participation in the project, and I'll talk a little bit about that. Acquiring different instruments, also thinking of advancing the state-of-the-art of the instrumentation, developing a roadmap on what instruments can be developed in the near term and be most valuable, and then also what's kind of the long-term plan for developing instruments. In the last couple months, we've been spending a lot of time on experimental design, and I'll show you what it looks like at the moment, using a lot of different simulation tools from LES to kind of lower order models of wakes in particular. And then also thinking about data management. How are we going to get all of the data from all these observations uploaded to a publicly available data set or website, and data not only from observations, but also from simulations that can be shared. So here's the location of the AWAKEN experiment. This is northern Oklahoma, and actually the top of this graphic is the Oklahoma-Kansas border. So in the central Great Plains of the United States, Oklahoma City would be southwest of this area. But there are a lot of wind farms in this area. They're actually building more. There's another, let's see, I think they announced another 1 or 2 gigawatts that will be deployed to the west of this area. So it's very windy. a good resource and lots of different wind farms. So the wind farms that we're really focused on, there are 5 here. They're all listed. You'll notice that all of these wind farms contain GE turbines. So GE, or General Electric, is a critical partner in this project, and 3 different wind farm owners. One reason that we chose this location is its proximity to a Department of Energy facility. There's something at the Department of Energy called the Atmospheric Radiation and Measurement Program, which takes a lot of atmospheric measurements. And this facility was actually constructed in the early 1990s to take atmospheric measurements, and well before wind farms were constructed in the area. These first northern wind farms were actually built in 2012. So we have a lot of observations from this facility before and after wind farms were constructed, and the observation equipment is still continues to take data and can be used in the AWAKEN project itself. Okay, so we have lots of different partners. This is a large project where we've kind of modeled the structure similar to the Perdigao experiment, which some speakers have talked about this morning. So lots of different entities across the US government funding national labs, National Science Foundation funds universities, and also the National Center for Atmospheric Research. There are a few proposals being developed in the European Union. One of them led by the Danish Technical University, Jakob Mann specifically. And then industry partners, so some of the wind farm owners are shown here, and of course GE, as I mentioned. We hope to continue to gather partners, and so if anyone in this meeting is interested, participation is still open and available to actually participate in the project. And of course, after we gather data, we do hope to do benchmark studies and release data within the continuation of this IEA task. So starting off, we have a series of testable hypotheses, and these are just shortened versions of the actual hypotheses. We have 7 different hypotheses that we're looking at, and a lot of them are fairly intuitive to the issues that are facing wind farm owners today. So wakes changing with atmospheric and operating conditions, turbulence within wind farms, blockage is a big topic. Wind farm controls is seeing a lot of interest, of course, the last couple of years, and there's a new IEA task specifically focused on wind farm controls. And then these last 3 here are more fundamental hypotheses looking at, you know, just the dynamic, often the dynamic fluid mechanics within a wind farm and how the wind farm interacts with the atmosphere. So we hope to gather data from all of these, for all of these different hypotheses in the AWAKEN project. Just one quick slide on the instrumentation development roadmap. So we've had many meetings trying to figure out the highest priority instruments that we could develop, say in the next 5 to 10 years, and where might make the most sense to develop those. And you can see just a list of many different instruments here. And actually this top table are for different goals for different projects, AWAKEN being the middle one. And then on the bottom here, we're listing technologies that have been developed or are in the process of development, and then thinking about near-term development of different projects. So for example, synchronized Doppler LiDAR, similar to like a wind scanner system out of DTU, or unmanned vehicles. And then in the long term, these are kind of long-range ideas that are not ready to deploy as of yet, but could be if they receive some development funding. And then as far as the experimental design, so these last 2 months is, as I said, we've really been focused on 4 different working groups. So those working groups are broken into wakes, so downstream of wind farms and turbines, blockage, which is upstream of an entire wind farm. Turbulence and loads are within the wind farms, and then wind farm controls, which is just a separate entity there too. From our current inventory of instruments, we know that we'll have over 100 different types of instruments deployed, and one of the challenges, of course, is kind of coordinating all of these different partners and instruments and even uploading the data. All of the instruments won't be deployed simultaneously, so there's some advantages to that actually, so we can have a slower deployment. But by the end of the project, we will have kind of a detailed deployment with all of the instruments simultaneously participating in the project. Doing lots of simulations and also thinking about getting access to different land lease areas. This graphic here on the right is an example of the experimental design from the University of Texas, Dallas. And here we have 20 scanning lidars placed within and around two of the wind farms that I showed you in the earlier graphic. And so this is really focused on wake observations within wind farms and how can we get the most coverage using all of these different lidars. So that just kind of gives you an idea of the scale of the project and the types of data that might be available in the future. Maybe a little bit more detail on the experimental design. So you could also think about it as 2 different scales, the large scale effects, which would be wind farm wakes. So how do all of these different wind farms interact with each other? And the size of this domain, I think, is something like 50 kilometers on a side, just to give you an idea of how close these wind farms are. And then also consensus control is a large scale control technique where the wind direction of each turbine is calculated based on information from all the surrounding turbines. So there is a consensus agreement on the wind direction itself, and that's been shown to improve the overall energy capture. But as far as wind farm wakes, you can see some thin lines here, thinking about different transects that we can make of wind farm wakes. And these would be done by both stationary and mobile observation platforms. So this will, the AWAKEN project will include things like aircraft, both unmanned and manned aircraft, to really be able to observe these large-scale phenomena. In addition to an X-band dual Doppler radar system, if you're familiar with the Ørsted beacon projects, we'll have an identical system deployed there. So we should be able to observe a lot of flow information in and around these wind farms here. You'll also notice a lot of instrumentation focused on this wind farm in particular, and that has to do with the scale, the small scale observations. So here we're looking at individual turbine wakes, blockage effects, loads, and wake steering, which is another wind farm control technique. We've chosen the southeast corner of this, the King Plains wind farm here. And again, just to give you an idea of all the different instruments that might be deployed. So different met towers and scanning lidars and tether sondes, which are balloons with tethers. And so, and actually individual turbines that are instrumented with loads information. So we'll be able to get that kind of data there. And yeah, I think that's all I want to say about that. So just to give you an overview of the project, here in 2021, it's more planning and getting ready for the experiment. 2022 is when we actually deploy the instrumentation out into the field and begin gathering data. We think then probably near the end of the year, we'll have some data that should be available to the IEA task continuation. And this campaign will continue for, right now it's planned for 21 months, so a long period of time, but the last few months of the campaign will really be focused on high fidelity observations. So this is when a lot of the more detailed instruments will be deployed, things like unmanned area vehicles that can't be sustained over long time periods. And then 2024 of this project is really all about data analysis and model validation and making sure that it's uploaded to what we call our data archive and portal for general public availability. So kind of not this year will there be a lot of activity for task 31, but certainly next year and the few years after that. So as far as how this community should be involved, you're welcome to directly participate right now, actually. So we've had lots of collaborative meetings. It's a fairly open planning process, and I've been having lots of people attend those. And then we're also willing to help secure some funding, so helping different entities write proposals, letters of support, and things like that. So if you're interested in actually deploying instrumentation or simulations for the project, we would like to open that up to anyone who's interested. And then once we gather all the data, we'll have many different benchmarks from all the different working groups. You can see here an overlap with the controls IEA task. And next year, I think there won't be too much data to share or benchmarks, but can probably start with code-to-code comparisons. And we've already been doing a little bit of that with the validation comparison to observations beginning the year after that. And then we'll have to think about how to fit in uncertainty quantification, which is a huge thing for both the observations and the simulations themselves. So I think I will stop there.
Thank you, Pat. This was very impressive. The design is really very encouraging. So is there any question from the group? Yeah, so I guess we are all just expecting to see some data and simulations. So looking forward to that too. Sure. I know you have been running some simulations already. Have you identified some phenomena that was not expected, or is everything more or less according to plan?
Yeah, so the one thing that is of concern at the moment is the blockage observations. We've been doing simulations of the blockage, including just small variations in terrain. There are small hills in the area, so maybe something like 5 to 10 meters change, and from the simulations that resolve the stability and in LES, it shows that just these small variations in terrain can actually overwhelm the blockage effect. So it will be hard to separate terrain effects from blockage in the observations. And so that was a big surprise.
Yeah, big surprise, but to some extent, you could have anticipated the challenge, right? Anyway.
Yeah, with blockage being a small effect, it's hard to separate it from the noise. Yeah.
Yeah. All right. Any other question? If not, then well, thank you, Pat, again, and I will take over and present the last part of the session, which is directly related to the next phase of Wakebench. So essentially next week, I will present to the EXCO the final management report. As soon as this is approved, well, we can close task 31, and then we can start discussing a follow-up proposal. We because of the way it works with AWAKEN, especially, I think it is on our interest to not start the next phase very soon, and maybe consider starting the next phase in 2022, so that we have more overlap with AWAKEN validation activities, and also to allow European projects to take form, and so we can have a better alignment with the IEA. If you would have national projects also planned in the next few years, it would be great to discuss with you how we could align those with the plans for the next phase. But essentially, this mind map that you see in the screen summarizes the different areas of interest that have been identified over a survey to the participants and also through different meetings. As you can see, we have, of course, all the discussion on phenomena of interest that Pat was very comprehensive about. This is related really to the scientific community mostly, and this is more or less a standard practice already for Wakebench. The framework is also there, so I guess we'll be adding more content to the framework and hopefully more on scientific quantification. But anything related to guidelines and best practices is what the framework is about. Concerning methods, which is what the industry also likes to see, we need to be more practical in how we document our processes and how we approach the industry in a more direct way. So anything related to methods for model calibration or how to bring machine learning into the process and so on. Those are very interesting topics for industry. And it's also interesting, of course, to engage with them. So we see here how we have the OWA as a very nice collaborator in the past. So why not engaging with them again for all of the offshore assessments and also with the IC working groups on wind resource assessment, site suitability, and of course, numerical site calibration. There is, of course, a plethora of IEA tasks that are very interesting to establish collaborations with. And I have just listed here a number of them with which we have good opportunities. Most of them are starting new tasks. So I think it's also a nice period in the next coming months to discuss with them more actionable collaboration that goes beyond joint meetings, so really do plan some work together. Yeah, but this is the value proposition I have put together. I don't know if you would agree, but build industry-wide consensus on adoption of a modulation framework and quality assurance criteria for engineering wind farm flow models used in energy yield assessment, site suitability, and wind farm design. So we keep the same focus on applications, but we are putting more effort into adoption of the framework and adoption by industry. I think this is what needs to happen for this to become really impactful. So that's why I put in front the engineering wind farm flow models, because kind of any effort in higher fidelity models should be directed into improving the actual tools that the industry is using. So some objectives, of course, the scope is going to be on modeling trends like multi-scale. That's a clear trend. Time series modeling is becoming more and more of an interest. And data science, of course, how we can improve our models by having more machine learning and other related techniques. We'll keep on doing more physics-based benchmark. I think those are well established, but we'll try to have more industry-driven benchmarks. I think this is how we bring industry on board. And then how to build consensus with them and try to get them define what kind of quality acceptance criteria it would be good for these models, what kind of targets in model evaluation metrics we should focus on. And then pathways towards standards. So these standards are all related to flow modeling activities, but they don't have a clear recipe on how to certify that the models are suitable for the applications of interest. So as soon as we get some engagement with industry, we should clearly target more engagement with the standards so that we have the framework referenced by them. This is a preliminary design where we keep the kind of a similar structure as before, but now instead of having two work packages, one for wind, another one for wakes, we dedicate the first work package to physics type of benchmarks for the usual stuff, and then the second work package to more application-related benchmarks, so more industry-driven type of activity. And then the work package 3, which has been always dedicated to documenting the framework and putting a comprehensive structure of the benchmarks, so now focus on adoption. So really, that's the key objective. The deliverables stay more or less the same, and maybe I would highlight that since now we are putting more effort into open source evaluation scripts, so I think we are in a good stage to come out with a Python library. This is actually a very fundamental tool for adoption, because as soon as you have something that can be used seamlessly across different type of benchmarks, it will become in itself like an actionable best practice guidelines that a standard could very easily refer to for metrics and other type of definitions. Concerning work package 1, all kinds of experiments, NIWA and Swift already known, but AWAKEN coming up very strongly, as well as X-Wakes from Germany on the offshore side of things. And we really cover all the scales and many different phenomena. So the challenge is not to get access to data, is really to organize so many validation activities that are of interest. So how to coordinate modelers to really engage in all of them will be the main challenge. Concerning the industry-driven benchmarks, as I said, we keep the collaborations with the IC groups, but maybe try to make them more close, and then also a new working group that is actually trying to put together a standard for model validation. So David Maniaci is in close contact with them, so we should also establish some kind of liaison with them. Also, we have the Offshore Wind Accelerator as a potential source of data. And concerning benchmarks, I see this more like case studies where we address yearly long type of measurements that from which we can extract annual energy production and site assessment quantities. And we can do this with public sites where the data is available, and we can have a more insightful view of the model evaluation process. But then, of course, there will be private sites like we had the case in the OWA, where we do more blind testing. And then it's the industry that takes care of the assessment, or someone in charge of the industry. And based on that assessment, we develop a common library that can be used by different industry players eventually. So out of this analysis, we should have a round of gap analysis. So based on the assessment, we should say, okay, here is where we have our largest errors. So maybe the validation activities should really focus on this and not other physical phenomena. So this type of data-driven approach to gap analysis would be very, very useful if we have enough sites and to complement the expert elicitation process that was going on in the previous phase. As I mentioned, the main topic for the framework will be to define this Python package for model evaluation, which I think it's going to be very interesting for academics, but also for industry to participate in. And that's it. I don't want to go